So that's why we move to quantitative and formal validation methods, approaches that use data and statistic to more serious test if a model can truly be trusted. So, and we are starting with very powerful tool, which is statistical hypothesis testing. Again, maybe you are familiar with a statistical hypothesis testing, so then just skip this one. If not, try to explore the information which is provided here. And plus, I would like to pay your attention that in our course, in a section dedicated to additional references, you could find out the part of the book which presents the basics or fundamentals of statistical hypothesis testing. So, but the overall approach is that we compare real data and model outputs using some statistical tests. In this case, of course, I'm not going to discuss all the tests which exists. We will focus our attention to three tests which are really very useful and popular. And the first one is a t-test, which compares means under normality assumptions. The next one is U-test or Mann-Whitney test, which compares distributions without assuming normality. And finally, the Kolmogorov-Smirnov test, which compares the entire distributions and gives a global view of similarity. So again, as I have stated, there is a quite huge amount of theoretical aspects related with the statistical hypothesis testing. I'm not going to explore it now in the details. If you are not familiar with this concept, please refer to the book chapter dedicated to statistical hypothesis testing. The only thing which probably I need to mention here that again we are really dealing with quantitative data, real data, and a data which is produced by the simulation model. So here is just a numerical demonstration of how we are applying statistical hypothesis testing. Just to remind you, we are talking about t-test, U-test, and Kolmogorov-Smirnov test. And again, as you're able to see, we have the output from model 1, we have the output from model 2, and we have the real data. So applying statistical hypothesis testing, we are receiving test value and we are receiving something which is called a p-value. And for us, it's really very important to understand of how a p-value can be used for a decision making about statistical hypothesis acceptance or rejection. So at example, for model 1, all p-values are really close to 0, so we reject the main hypothesis that the model is statistically different from the reality. While for model 2, all p-values are high, so they are above the specific significance level, meaning that we find no significant difference between the model and the real system. So therefore, the model 2 can be considered statistically acceptable. Again, guys, for some of you who are not familiar with statistical hypothesis testing, I would really recommend to refer the additional material, but also I would like probably to promote a bit that please refer to tutorials which provides much more practical advices about statistical hypothesis testing and even explains much more nuances about statistical hypothesis testing. So if you feel that statistical hypothesis testing is too complex, I would propose to see the following one more test, which is called a confidence interval testing. So a confidence interval testing checks if the model and real system are close enough. So we compare the mean of real data with the mean of simulated data by building a confidence interval for their difference. So the key rule is really very simple. If the interval includes 0, there is no statistical evidence of a difference. If the interval does not include 0, the model differs significantly from the reality. This one is really very simple rule. So, short numerical examples regarding the confidence interval testing. As you're able to see, we have two models, and we are going to apply a confidence interval testing for the two models. So, talking about the model 1, what we are able to recognize that for model 1, the confidence interval for the mean difference does not include 0. So the model statistically different from the real system. For the model 2, the confidence interval includes 0, meaning there is no statistical evidence of a difference. So based on this test, a model 2 is acceptable while model 1 is not. Okay, so now we are moving to the next slide, and here actually we are representing specific group of the measures which are error-based validation measures. So you could see several of them. As example, the absolute error, which shows how far a single prediction is from the reality. You are able to see mean absolute error, which gives the average error across all observations. You could see mean absolute percentage error, and you see root mean squared error. So the formulas are indicated here. They're really not very complicated for understanding. And again, guys, I would like to pay your attention that it will be some tutorials dedicated to error-based validation measures. But in the same time, for students who prefer to deal with the traffic flow simulations with transport problems, I would like to promote a domain-specific metric or domain-specific measure, which is indicated here. It's called a GAX statistics. It is used for as a traffic validation metric. Again, an equation by itself is not really very complicated. And you see that there are even some recommendations. So if the calculated value is less than a 5, so it's a good match. From 5 to 10, acceptable. More than 10, so it's a poor fit. And again, the following equation or the following measure is actually the domain standard. So guys, again, if you are dealing with a traffic flow simulation, of course you could calculate root mean squared error or mean absolute percentage error. But to be honest, if you would like look in a professional way, so in this case, a GAC statistics shall be calculated. Okay, to summarize, start with face validity. Does the model look realistic? Always validate both structure and data assumptions. Compare model outputs with real system KPIs. Use statistical tests and confidence interval for formal validation. Please pay attention that a naïve method is really very attractive because it's a simple one, but in the same time, please do not apply it alone and do not make decisions based on a naïve application. So the last two statements, which, sorry, I will remind you that validation doesn't prove correctness. It shows credibility for a specific purpose. And of course, the strongest validation combines data evidence with expert judgment. So try to utilize all spectrum of validation techniques which we have just discussed.